Well, good afternoon. I think we're gathered. It's lovely to see you. Welcome. My name is Sandy Moose, and I'm a senior associate of the Graduate School Alumni Association Council. And I'm delighted to be with you today and to introduce our speakers, Professor Stephen Wofsy and Professor Emma Rothschild. Stephen Wofsy is Professor of Atmospheric and Environmental Chemistry at the John A. Paulson School of Engineering and Applied Science at Harvard University. I'm going to have to read this as it gets more dense in terms of your research. He has degrees in chemistry from the University of Chicago and received his PhD from Harvard in 1971. His scientific work spans the broad range of processes affecting the chemistry of atmosphere, including measurements and inverse modeling of emissions of carbon dioxide and methane from ground-based aircraft and remote sensing measurements. The work spans spatial scales from ecosystems, for example, 30 plus years at the Harvard forest, to regional and global remote sensing. His studies aim to understand underlying causes for changes in atmospheric composition in order to mitigate human impacts and to help provide scientific information for societal decisions. He is the lead science lead for MethaneSAT satellite and MethaneAIR aircraft imaging spectrometers to measure methane emissions worldwide. He's a member of the National Academy of Sciences, and he is the recipient of several honors and awards, including NASA's Distinguished Public Service Medal. So thank you. And Professor Emma Rothschild is the Jeremy and Jane Knowles Professor of History at Harvard University and Director of the Joint Center for History and Economics at Harvard, the University of Cambridge, and the Sciences Po in Paris. She's the author of Paradise Lost, The Decline of the Auto-Industrial Age, Economic Sentiments, Adam Smith, Concordat, and the Enlightenment, and An Infinite History, the story of a family in France over 3 centuries. She coordinates the 1800 histories of methane projects. So please join me in welcoming both Professor Wofsy and Professor Rothschild to begin their presentations. And thank you so much for spending time with us.
Thank you very much. So it's really wonderful to be here. I'd like to thank the organizers for inviting me to come today. And we're going to tell you about a number of different projects. But I really would like to make it a conversation. I've been invited to stand to do this because I guess people in the back can't see me if I'm sitting down, but I would be perfectly happy just to be sitting here and having a conversation. So while we're talking about this, if you see something that you want to know more about, or if you would like to converse about any of it, just either raise your hand or shout it out if we don't see you. And that way we'll get into more of a conversation than just Emma and I lecturing for 75 minutes. This can be pretty boring. So the collaboration between myself and Professor Rothschild arose through some interactions in the Harvard's Salata Institute for Climate and Sustainability. So, I'm a pretty hardcore physical scientist and engineer. Emma's a historian, but actually very technically astute historian who has very broad interests. And we were introduced to each other through the Institute. And you're going to hear a little bit about, what's in common between a historian and somebody doing remote sensing of the Earth. So we'll get to that. So first of all, we're going to talk a little bit about atmospheric methane. I'm not going to bore you with a lot of information about it. I'll just show you a few little things. So here's a graph. On the x-axis, there's the year, and on the y-axis, we have the concentration of methane in the atmosphere. If I were to draw such a graph, I could actually take it back in time all the way almost through the last million years, because we can extract methane from the air that's trapped in glacial ice, and we can reconstruct the history going back in time in that way. And a lot of this graph is made by looking at data taken from the ice, except for the stuff that turns blue up there. Those start to be data that are actually measured in the atmosphere. And what you can see is that the concentration of methane in the atmosphere has approximately tripled since 1000 AD, and that the increase started somewhere around the late part of the 18th century. And this is quite an extraordinary thing that's happened because methane is the second most important trace gas in the atmosphere. So the major gases of the atmosphere, oxygen, nitrogen, and water. And then you have some noble gases, and then you have the trace gases which are chemically and biogeochemically active, as CO2 and methane. Methane is number 2. And human, yes, please.
I assume your two methods of measuring are commensurate.
Yes, because people worked actually very hard on this problem about whether you could recover the air without modification from ice that's 100 years old or 100,000 years old. And that problem has been solved correctly. And then the measurements themselves are actually made the same way. You use a gas chromatograph or you use an optical laser system, and the measurement of methane is fine that way. So in the case of these older samples, the issue is not so much the measurement of methane, but whether you can recover a sample that hasn't been modified. And as I say, people spent decades working on that problem, and that problem has been solved. So that's a good one. Oh, thank you so much. I can really use that. Okay, so and I put a few milestones on here. So we went from about 680 parts per billion to 1,000 between the end of the 18th century and 1945, the year before I was born. And then by 1975, when I began my first time on the Harvard faculty, it had already gone up 40% over my lifetime. I was a lot younger then. And then to the current time, it's approximately increased by the same amount, but since 1975 and the current time. So this is a problem. Methane is quite important in the atmosphere. It's the second most important greenhouse gas as influenced by human beings. So a greenhouse gas is a gas that enters the atmosphere and absorbs heat radiation coming from the Earth and radiates some of it back to the surface of the Earth, warming the Earth. So as I add more greenhouse gas, I get a warmer planet. The most important greenhouse gas by far is water. And the most important greenhouse gas under human control is CO2, and number 2 is methane. And it's actually quite an important gas. So we're really doing something there. Methane is also chemically active. It does all kinds of things in the stratosphere and the troposphere that we don't need to discuss. So why has this happened? So I'll give you a little bit of an idea. So it hasn't happened for one reason only. So this is a little budget. So for those people who like pie charts and budgets, this is basically saying every year on average about 550 teragrams or 550 billion tons of methane enter the atmosphere, and a little bit less is removed each year because it's going up, but there's almost a balance there. And so we can then ask, okay, what is comprising that 550? And we look at the pie chart. You got wetlands, which are natural to some extent. They may be disturbed, but they're natural. Everything else is under human control. Livestock, most of the fires are human controlled. Agriculture, beside livestock, is rice agriculture. Oil and gas and coal representing the fossil fuel sector, and waste, which is really landfills. Methane is produced by anaerobic activity in soils and organisms. So cows have segmented stomachs, which host bacteria that can digest cellulose. And since it's anaerobic, you can have bacteria there that make methane, and they do. And so that's where the livestock come in. And very similar processes happen in the bottom of a dump, right? There's the water full of water and a lot of organic matter, and you generate methane there. The oil and gas, some of it is generated that way and trapped. Some of it is actually created from other organic matter by geological processes, but we're releasing it to the atmosphere. So something like 2/3 of the total budget of methane in the atmosphere today is under human control. So what we don't know actually, these numbers, I actually really like pie charts, because what I love about pie charts is you cannot put error bars on pie charts. So you have no idea how uncertain these numbers are, but they are actually quite uncertain. So, and they can be made very pretty like that. But so about 2/3 of the methane that enters the atmosphere each year is under human control. And we have every reason to want to try to bring this in. So I could tell some, excuse me, I could tell some, I'm going to have a sip of water here, just a moment. I could tell some funny anecdotes about methane in the atmosphere. If I go back to that period in the 1970s, when it was increasing probably the fastest that it has been during the entire period, at that time, people didn't think methane was changing in the atmosphere. And there were some interesting debates between people who had made the measurements by different ways. And one had gotten a higher number than the other. And the debate was who was right. And they were actually both right. It was changing so quickly that the measurement made 10 years earlier, it was lower. So it's really quite an interesting story. So the rest of the discussion is going to focus on the question, where is this all coming from and why is it being emitted? So there's one thing you can think about in terms of our efforts to rein in climate changing gases released to the atmosphere. When we burn fossil fuels to make energy, we get energy out of it. The energy runs the modern economy. But when we release methane to the atmosphere, we get nothing for it. Nobody benefits from that. And to the extent that we're losing methane from a fossil fuel value chain, we're losing a valuable resource. So it's a waste. So it's actually economic cost. For the agricultural sectors and the waste sector, so it's arguable that anybody would benefit from that. So why is it being emitted, and how do we stop it? So one tool that we need in the toolbox of how we might reduce this waste, I'll get to you in 1 second. One tool in the toolbox is understanding better where it's coming from and why it's being emitted. Please, what's your question?
Is the main problem with methane is that it runs up the atmosphere, or does it also contaminate?
Yes, the main problem that people like to focus on is that as I increase methane concentrations in the atmosphere, like any greenhouse gas, heat radiation that's trying to leave the surface of the Earth and go out to space is intercepted, and about half of it is radiated back to the surface, heating the surface. And methane is very efficient on a per gram basis or molecule basis. It's about 20 times more efficient than CO2. So even though the concentrations are lower, that increase that you see accounts for something like 1/3 or half of the human-caused changes in that radiation. Yes?
Are the emissions from coal, oil, and gas from those elements, those things themselves, or from their consumption and energy production?
That's a really good question. So the question was, is the gas being released to the atmosphere during its consumption, or during the production and transmission, processing and transmission? And the answer is yes, both. And this is part of the conundrum that we have. We don't really understand all of it. So as you'll see, we've surveyed a lot of oil and gas fields. We're not the only ones who have done that, but we have an airborne simulator for the satellite. And some of these are emitting enormous amounts of methane to the atmosphere. Others are emitting much less. And it's not fully understood why that is. There are engineers around who work for the companies who may have a good idea, but in fact, some of what they're doing, a lot of what they're doing that releases methane, they don't really know. They know they're releasing some methane, but they don't know how much. And they generally don't care unless they're invited to care. Yes?
Methane.
Yes. So when you turn on your stove and it goes poof, Yeah, there's some methane is released there. There's been some really nice studies of that problem in the home. It turns out most of the stoves that you have, much more methane is released when the gas stove is off than when you're using it. And that's because they use cruddy little fittings in your in the valves and whatnot. And methane and natural gas is released that way. A lot of methane seems to be released from in some jurisdictions from heating large buildings where you have very large boilers. And they're not tuned up very well, and the gas is cheap. And like New York is notorious for this. It has a lot of the heating plants in their large buildings originally were designed to burn bunker fuel. You know what bunker fuel is? It's what they use in ships. And so they retrofit this. They can't do that anymore, so they retrofit it to use natural gas. And you look at these things and you say, oh, it's not Stone Age, it's sort of Copper Age. It's like, wow. But so all of these things happen. And then when we go and we fly over natural gas electric generating stations, most of them are not emitting very much methane from the stacks, but from the LNG storage tanks next to them, they might be emitting quite a bit. Some of them are. So, yeah.
Sorry, you say that these the gases are dangerous because they trap the heat that normally would get reflected back. If CO2 and methane didn't exist in the atmosphere, more heat would be radiated out into space, right?
So it's not quite that. I don't want to get too.
My real question was, if methane absorbs heat, is it the methane in the atmosphere that gets hot?
So how can I best describe this? If you stand in front of a hot fireplace, you feel the heat on your face. That's radiant heat. Take a piece of newspaper and put it in front of you, and you don't feel as much heat. Where did it go? And what's happened is that the newspaper has intercepted the heat. It has warmed up, and it has then radiated some of the heat back to the fire. So the fire has actually gotten a little hotter, and you're feeling less heat on your, and methane is acting the same way in the atmosphere. So it does warm the air around it, and that also affects the physics because there's water there, and so the water has gotten hotter.
But it's the actual methane molecules that are getting hotter.
Yes, but then they also,
and then all the air around it gets hot.
that's right. And so you get radiant heat from the methane molecule itself, and you also get additional radiant heat from the other molecules that are being warmed in the layer next to it. So both are happening. Okay, I'm going to need to move along. So MethaneSAT is a satellite project that's intended to make measurements that are currently not being made to inform the world about where methane is being emitted and why from the oil and gas industry mostly, although there is an agricultural component of the project as well. And so this project was spun up between myself and Steve Hamburg at the Environmental Defense Fund and some other people engaged in that process in the 2015-2016 time period. So the goal of MethaneSAT is to be able to look down on the Earth, look at oil and gas provinces or other places of interest like landfills and whatnot, measure the emission rates, and also measure the emission rates from large areas that are involved in the oil and gas value chain. Because people are well aware that you can see if there's a blowdown at a big compressor on a pipeline, you'll see that. It's huge. It doesn't last very long, but you see it. And so if you can reduce those, you can reduce the amount of methane entering the atmosphere. Quantitatively, however, it does appear that a lot of the emissions coming from oil and gas production areas are coming from much smaller, innumerable, much smaller leaks or ventings or other ways that methane is escaping into the environment. And we need to quantify those, understand where they are, and figure out why that is. One class of sources is abandoned wells, of which, are you going to talk at all about abandoned wells?
Yeah, a bit. And on the point about where it comes from, abandoned coal mines, long closed coal mines
Right.
continue to emit methane.
That's right, especially in China. I don't know if you're going to speak to China, but there's thousands and thousands and thousands of small-scale coal mines in China, many of which have been abandoned in the last period, and some of those will be emitting quite a lot of methane. So understanding how that is working is what we will need to do if we're going to arrest that rate of increase. So MethaneSAT is going to make some measurements. I'm going to show you some examples of the measurements that we've made using the airborne equivalent of MethaneSAT, and you may be very surprised at what you see. So the project is involved advanced science and engineering. As it turns out, when we did the feasibility study, I thought we were making a conventional imaging spectrometer, and it didn't turn out to be quite right. It had to be considerably advanced. The data are all going to be freely distributable, and we're also going to try to make actionable data products, which means some of the wonky science stuff that I'm going to show you is going to look much better and would be much more accessible to real people. My definition of a real person is a lawyer. So we're going to try to make it accessible. There is an advocacy program that goes with this. It's not here at Harvard. It's an Environmental Defense Fund. It's funded by private philanthropy. And you say, well, wait a minute, private philanthropy doesn't fund satellites. This is the first one of its kind, as far as I know. There's another one also in the methane space that has some different architecture and some different objectives for how it's going to make the measurements. Are actually quite complementary. It's also funded by private philanthropy. And the point is that when you fund it by private philanthropy, you can take it all the way from the physics and engineering right into the boardroom, right into discussion with advocacy groups, with government groups, with the industrial players and whatnot. You can't do that in a national space program. You really shouldn't, and you can't. But so we wanted to do that. So that's why we're doing this. And the EDF was able to raise a significant amount of money to do it. Here it is. It's real. It's shown up there on the upper left-hand side. And the airborne version is shown here. So that one flies on the Gulfstream 5, which is an NSF airplane. So NSF has stepped in to help us fly this thing. So there's a picture of the NSF airplane. EDF also funded the purchase of a Lear 35A, wonderful 1977 vintage business jet. And there was a modification existing for this. It was the first plane of its type to be made, and DoD wanted to be able to use it for remote sensing. So there was a modification that dates from the 1980s that we were able to use. You can't make your own modification at reasonable cost and time, but there it goes. All right. So MethaneSAT was launched on March 4th, and there it goes on a SpaceX airplane, SpaceX rocket. That's what it looks like. It's bigger than it looks, right? So those are full-size tanker truck loads there, and those little white things on the left side. So it's actually not that small a rocket. And it's really science fiction. This thing takes off. There it goes. Up it goes, up it goes. And that's when the first stage is just about to finish its burn. It lets the second stage off. And then that rocket flies back to the launch pad. And 7 minutes after the launch, it lands back where it was, just like you setting down your teacup. It was quite an amazing experience. 2.5 hours later, our little guy goes. So there were 100 or so satellites on here, 55 different payloads to be launched. They're all gone. There's one left behind us, and that's MethaneSAT right there. This was a key moment. Our little friend is gone now. And then finally, off it goes. Great relief. Okay, so the last few minutes before I turn over to Emma, I'd like to tell you about some of the measurements that we made. This shows where we took that Learjet last summer. And we were hoping to turn these data around and make them all public and whatnot very quickly. That didn't happen for a variety of technical reasons. It's all done now. And I'm going to show you a little bit about this. But this covers something like 80% of the onshore oil and gas production areas in the United States. Yes.
I'm sorry, I missed the connection between the satellites and the Learjet.
Okay, the Learjet has a spectrum. I'm sorry, right, I skipped over that. The Learjet has a imaging spectrometer on it that has exactly the same spectroscopy, not exactly, but very, very close spectroscopy compared to the satellite. So the images that we get from the airplane are strictly comparable to the images that we will get from the satellite. They have a smaller footprint. So it's still pretty wide for an airborne imaging. It's about 5 kilometers wide from 40,000 feet. And an individual pixel is 20 meters on a side. The satellite will have an individual pixel 100 meters by 400 meters on the side. So it's still pretty small for a satellite. But the images that we get are strictly comparable. So when I show you what we're going to get here, with somewhat lower spatial resolution, that's what we'll be seeing from the satellite. And it's just kind of fun to look at these. So this is a composite of 2 hours of flying. It's a Zamboni pattern going around like this, and we fill it all in about 2 hours. This is the Permian Basin on the Texas-New Mexico border. That's what that black line is there. And the colors represent how much methane is in the atmosphere. And you can see there's a lot of excess methane in the atmosphere that doesn't belong there. So up on the upper left-hand corner, it's pretty clean atmosphere. The rest of it is perfused with methane that's coming out of this oil and gas field. This is the way the Permian always looks. You can see some really big sources with plumes extending 20, 30 kilometers in space. And yeah, so why does it look that way? That's what we want to know. And how much is the total? And I can tell you that this little guy here represents about 100 tons of methane per hour being released. This is only part of the Permian. And 100 tons of methane per hour is roughly a little bit less than 1 million tons a year. You got that? Yeah.
Can you explain how wetlands emit methane?
I can. I'd rather get to that a little, if we can, at the end, because I mean, basically, yeah, I'll say very quickly that wetlands, because of the water is covering the surface. If you have emergent vegetation, it dies and the stuff falls down in there, and it's much harder for oxygen to reach that environment for the bacteria to decompose that organic matter and turn it back into CO2. So the substrate, the muck under a wetland is anaerobic, and that's where you get fermentation, and fermentation is the process that produces the methane. The reason why wetlands are so important is that they're usually pretty shallow water layers, so the methane that is produced can get out. And some of the plants ventilate their roots, like rice plants in particular. So they're like little tubes that go down and release methane through the stem of the plant. So that's how they do it.
Is this available at the Salata Institute, this presentation?
Say what?
On the first page, you cite this Salata Institute Climate Seminar. Is the whole presentation the same as the first page? So available at the Salata Institute?
This is slightly different than the one that is on there. It's similar to that one.
Okay, so is a version of this in the public domain and accessible? By
A version of that is available at the Salata, and if you want this one, let me know. I'll send it to you. All this is public. Okay, this is some examples here. I'm going to step through because we're running out of time. This is an example of what we see from the airplane. This is a well pad. Gosh darn it. Okay, that's a well pad there. You can see that with the airplane, you can not only tell that the emission is happening, you can tell how much. That's about 490 kilograms per hour. And you can even tell what part of the well pad it's coming from. We won't be able to do that with the satellite, but we'll be able to do quite similar thing. How many of those do we have? Well, more than 400 of them in more well pads. These are different. This is a compressor station. The one on the left there, I think, is on an interstate pipeline. Landfills, there's your landfills. The one on the left there, Tower Landfill, right near the Denver airport. That's doing about 1.5 tons of methane per hour being released to the atmosphere. The one on the right, Denver Arapahoe, that looks like the whole active face is releasing methane. Other landfills don't emit very much. This one is one of my favorites. It's the Seneca landfill in Harmony, Pennsylvania. It's emitting about 2 tons of methane per hour. It's one of the champions for the ones that we looked at. As it says on the website, the Seneca landfill is a cutting-edge facility that's serving the needs of customers through Western Pennsylvania and Ohio. There's a wonderful YouTube video by the owners of this saying that they are in the business of producing renewable natural gas. Yeah.
These are methane measurements from your
From the airplane.
satellite or the airplane.
From the airplane, yeah.
From the airplane. And so it's seen all of the methane between from ground all the way up. Right?
Yes.
And I'm surprised these don't get dispersed more than that.
Oh.
Do crosswinds determine how?
So it is being dispersed very quickly. So as it's coming out of the ground, the gas from a landfill is about 50% methane. So if you lit it, it would burn. And you can put it, if you tune a diesel engine and put a little diesel fuel in with it, you can use it to drive a diesel engine. So it's getting dispersed very quickly, but we have a really good sensor. Does that answer your question?
Yeah.
I can even show you where it's coming from. It's coming from here.
If the wind speed went from 5 miles an hour to 10 miles an hour, would this picture change?
Absolutely. Yeah, a lot of these images, in the summertime in particular, you tend to have pretty light winds and you can get quite a blob of methane building up over there. But there's a very quick dilution by about a factor of 100,000. So you go from 50% to 500 ppb very quickly.
And the methane is lighter than air and rising.
Yeah, it's lighter than air, but first of all, in this case, it's coming out of a landfill, so it's half CO2 and half methane, which is actually heavier than air. The mixture is heavier than air. And secondly, once the methane starts to mix with the air, it's the fact that it has a lower molecular weight doesn't matter. It's all mixed. It's mostly air. So this excess is of order 1 part per million, or it's even less than that. It's about 1/3 of a part per million. There's 1.8 part per million in the atmosphere. So it's about a 15% increase in the amount of methane, but it's still very, very dilute, right? It's less than 1 part per million. So it goes very quickly from that concentrated gas to something that's not combustible. And so you don't usually have fires in these places. You can, though. They can burn. And this place, I'm going to have to skip ahead quickly here. Sorry.
Steve, is that by any chance a repurposed open pit coal mine that's now serving as a landfill?
How did you know?
I don't want to explain here, but
that's
I'm from Western Pennsylvania.
Okay, that's exactly what it is. And so in addition to this problem, it has all kinds of other problems, but yes, that's exactly what it is. And they have an advanced methane capture system, and when you put a hole in the system like this, it really accelerates the amount of methane that comes out. And this is a landfill. It's not an industrial machine, so it's moving all the time. It's breaking up these pipes. It's making holes next to the area here, and they leak like crazy. I'm not going to spend too much more time talking about this because Emma's waiting for her turn, so I'm going to page through all of this. I think. Emma, I'm ready to turn this over to you now if you're ready. So what our project is about is combining this sort of thing with understanding why it's there. And you put your finger on it right away, right? So that's a repurposed coal mine, which brings in all kinds of other things with it. By the way, they also had methane, they had natural gas recovery around the coal mine, so they were mining the methane from the coal itself. And all that stuff is abandoned. And guess what? All right. But I'm amazed that you knew that. That was my punchline, you know. Like, okay. So at this point, I think what we do is we switch to Emma's presentation. And to do that, I'm going to sit down. I'm going to end this show. And you want me to bring up one of these. Do we know which one it is?
Why don't you bring out the one which has the data we just looked at, which is this one, emissions data map. Well, thanks very much indeed. I think the title that was given to this talk was Why Harvard Scientists Are Putting Up Satellites and Why We Should Care. So I guess I'm why we should care, which is the role of the social sciences and humanities. But Steve has already explained extremely compellingly why we should care. So I think what I want to talk about a bit is, and I really want to show you some of these maps, is where the methane is and what it means in a way. This is a map, and I'll explain the other dots, but the blue dots in North America are the, I guess, are you going to be the technical assistant here?
Yes, I am.
We'll sort of zoom in a bit down here. No, out. Sorry, out. Sorry. Plus here. Okay. You can, that's the Permian Basin over there. And what the project consists of, we're going to make a zoomable, usable map, initially of North America, of the United States, with the MethaneAIR data, and then sometime next year of the whole MethaneSAT, a worldwide map of the emissions that they see. And the idea is that you'll be able to basically click on a location, see what's going on there, see a photograph see some of his images, see actual photographs of the site, and eventually have a short, what we call microhistory of the place and why the methane emissions are happening there. And in some cases, I think Seneca Falls is an example, the history actually goes back well into the 19th century. So if we can go to one of the other, can we go to 1800?
What do you mean by history? You didn't do this 100 years ago, so where does the data come from?
Well, that's what historians think about all the time. There are archives, there are old newspapers, there's in many cases there's a regulatory history if there was a coal mine. So it's sort of figuring out a story of why this particular environmental and climate problem happens to be in that place. So, oh no, this is too idyllic. Let's go to the big map. Yeah, this one, okay. So we actually, independently of Steve's project, made this map using much lower resolution satellite data from the Tropomi instrument on one of the on Sentinel-5, one of the European satellites, and it's I mean here it's each of these dots indicates an area of 15-kilometer radius, so it's much less powerful than what Steve has produced with MethaneAIR. So these are what the French scientists who worked on the data call ultra emission sites, and some of them are very, very large indeed. You're really happy to do. I can sit there and do all this zooming in and out. Well, I guess I can. This is, no, sorry. Wow, I'm not very good with your computer, I'm afraid. Sorry, here we are. This is Dhaka, Bangladesh. Some of the landfill sites there are emitting 400, and in one case 400, in one case even 500 tons of methane per hour. So this is a very, very large problem. And I mean, what I'd like to do really is suggest that people look at the larger map and see some spots that you might be interested in, and we'll look at them. But you can see there are kind of interesting patterns of sort of spatial patterns. What you have there, you can see a sort of arc of red. The red dots are oil and gas estimated to be oil and gas related emissions. That big arc across central Russia corresponds to a pipeline, one of the big pipelines going to Siberia. The green dots are so-called human sites, and the orange, the yellow are coal. And you can, we wanted to look at China. Gosh, it's very different. Sorry, I don't know. So you can click on a site and see what the date of the observation and what's going on. But the history part of it is rather different, and that is to actually have specific histories of one of the sites. This is one of the Bangladesh sites by. These photographs are actually taken by a Harvard Econ PhD student. We've got quite a lot of small histories of Ukraine by a Ukrainian PhD student here is going to write a history of each of the sites in the territory of Ukraine, and then you can, and then there are sort of mysteries. I don't know how to work your computer. I really don't.
Can I help?
Yes. Can you get us to Houston, Texas?
I think so. I think I know which interstate that is.
A lot of you can see a lot of oil and gas related in the Sahara, the Algerian oil industry there. Great. Zoom really close in to Houston.
Yeah, I don't know how to use my computer either. I need a mouse.
Yeah. You see how much there is in the Mexican oil industry. Okay,
Right.
Houston, all right. There are a ton of ultra-emission sites in Texas, but almost all of them are in the sort of dusty western part of the state. This is the one.
Yes.
Zoom in on,
This one?
yeah.
This one here?
There's only one in the whole, well, actually basically only one in the whole United States, which is in a prosperous suburb of a major metropolitan area. So this is a kind of mystery. Why is...
I'm getting there.
Yeah, here we are. And just zoom in as far as you can go on that dot. And this is substantial. I mean, 53 tons per hour. This is a big ultra emission site on October 2020. So here we are. What could be going on there? It looks nice, leafy area. Any ideas? Well, the answer is really surprising, and I'm telling you something that's about to be published on the site, and I'm very nervous about it. And one of the fascinating things about doing this work has been when you do zoom in to the particular places that are so important in the genesis of climate change, you see how many possible causes there are. Even in a sort of extremely salubrious place. Now this is...
Why isn't it just a gas leak?
Sorry?
Why isn't it just a leak from the gas line?
Well, that is, after consultation with Steve, that is my best probable answer, although it happens not to have been noticed or notified. And this is a very, very large. So the sort of thing I did in this microhistory was find where the gas lines are. It turned out that there was an intersection, which is one of the places where pipelines are, an intersection of two, one of the places where they're particularly vulnerable to leaks. But there's quite a lot else that's going on. There's a big landfill site near the George H.W. Bush International Airport. There's a big railroad intersection, which has had a number of significant industrial accidents. If one goes further south we don't need to, in Texas, as people here undoubtedly know, there's a lot of environmental pollution in the sort of poorer parts of the town where the petrochemical industry is. So as it go back to our dot, does this really not mean anything to anyone, this geography? No Houstonians. This, our dot, and remember, it's the center of a 15-kilometer radius circle, so almost certainly it was a pipeline leak somewhere over here. But at the center, which is on a nice creek called Spring Creek, this is...
Space?
Nope. Global headquarters of ExxonMobil. It's a beautiful campus, built to the highest environmental standards. All these buildings have names like Science and Nature. And my belief is that it's complete coincidence that, sorry?
It's a laser pointer if you want.
Oh, thank you. Complete coincidence that this really significant ultra-emission site is just, a few steps literally from the Exxon campus. But this is historians digging. There are published maps of tapped oil and gas wells in Texas. And it turns out that there are a ton of them under this campus. So, I think it's very unlikely, but, it gives, working on this project gave me a real sense of the sort of depth of the methane problem and how it's sort of embedded in much larger questions of environmental pollution. So I think what I hope we'll be able to do with our eventual maps is something that's complementary to what Steve was talking about in relation to the boardroom. Actually have something that enables individuals in the communities affected to complain about the methane emissions, because the other thing that comes out so clearly from these historical inquiries is the extent to which methane emissions are co-located and co-emitted with other forms of environmental pollution, which are much more dangerous to human health, child health, human and other, including child health, and loss of amenity. And this is much more, this is much clearer in some of the Ohio sites, in many of the Colorado sites. So I think that's the hope, and it's it will be the maps will be a complementary way of bringing this data to sort of meaning for people involved by it. I could go on and on, but I think what I'd kind of like to see if we can kind of look at any of if anyone's interested in finding any of finding out more about any of the sites. I've got, if we have time, or if anyone's interested, there's another mystery site in the Lake District of Eastern Bavaria, a great beauty spot where there's another ultra emission site in the most implausible spot. But let's think about how both of these can work together.
So are you leaving us with the idea that this is just a mystery? You have no idea what that message is?
Well, no, I said it.
Is the pipe leak the operating hypothesis, or you said that there was more stuff going on?
There are a lot of possible explanations. Look, I think this is a mystery that can be solved. I don't think, how much was it? It was 53 tons per hour. That's a very substantial emission event. I can't believe that I couldn't, if I went to Houston and dug around and talked to the EP. People, remember, this is, this European data we're talking about, we're in mid-COVID, okay? So something happens in, this is October 2020, something happens, it's picked up 864 kilometers above, and it's transmitted to Darmstadt, wherever they're, people, it wasn't the sort of peak moment for environmental regulation in Houston, Texas. It was pre-election year and, election period. I don't know. I think, when I do publish this, and this is the sort of first outing of it, I guess someone on the Houston Chronicle will be able to talk to the pipeline operators if they want to. But I think for our purposes, it's a way of showing that there are complex environmental difficulties in many, many different places. Methane, in some of the kind of more abstract policy literature, methane is described as a kind of low-hanging fruit of climate policy. And if we had a 4.5% tax, then it would vanish worldwide. I think by looking in detail at the sites, including the landfill, but also the wetlands and tropical peatlands, which don't show up in these very concentrated emission data, I think it becomes more realistic to think of place by place policies to reduce the problem, as well as global regulation. Yeah.
What?
First, I want to congratulate you both, because I'm someone who's working on making those changes happen, okay? And this is the most exciting work. The satellite is the most exciting work that's happening worldwide, okay, on the methane problem now, okay? So we can pin it out, okay? Because depending on the context where you are in the U.S., under the new rules, okay, or you're in the developing countries where I work, okay, you've identified the source, okay? But every source of that in today's calculus is an opportunity for a business, okay? And where I suggest you do your next presentation and bring somebody else in, okay, is at the business school session of the Salta Climate Conference in June, okay? Because every one of those alternatives, okay, I can tell you some stuff that I know and I'm doing and other people are doing, okay? And there's an argument for figuring out what that is, okay? Because depending on the price you want to put, okay, just on reducing, okay, the methane emissions, which is so important. He used 20 times methane. One of your figures here has got 25,000. EPA is now using as much as 80 because of the short-term measure. Right. And that's in all just in terms of the value, in terms of the environment, okay, in global warming, in terms of the methane. But if you start to look at agriculture, okay, and landfills, okay, and you can pinpoint where those landfills are, and I can tell you about cases that I'm doing and financing personally with my NGO now and social investments, okay, when you can keep that carbon from getting in that landfill, okay, and you put to work on it, okay, insect engineering, okay, and that carbon-rich waste, okay, that's not going to be digested, okay, anaerobically, okay, but in fact is going to be digested, okay, with belt bugs and other stuff, okay. You are now connecting it to the food chain, okay, and you can feed it for growing chickens or something else like that. And I'm telling you that those solutions are there, okay, and they can be done at large scale if you put it all together, starting with I think he called. How did you characterize lawyers? Okay, You not only got to characterize lawyers, you got to characterize businessmen together to do an environment, okay, and if you would, business. In terms of what I do, it's environment, poverty, and business, okay, and that's a consequence. And you have solved a gigantic problem for the world, okay, because you have identified a way to find these spots all over the place. And when you have those spots, somebody will have enough initiative to figure out why that spot is happening. Is it that leaking? And it's obviously, the low-hanging fruit is now happening already. There's people looking at leaking wells, okay, that we know where the well is. If I were here in America and doing stuff like that, I would start to do a business now because you know how to do it. I'm hooked on poverty, okay, and doing other stuff in India. I've been on that dump in Bangladesh, okay, and I've been on a whole bunch of those other dumps, okay. This is miraculous what you've done. This and the satellite is just miraculous, and it's going to change if we put the rest of it together, okay. And so this is the most exciting. Look, when the article came out in the Times about the initiative and the satellite, okay. I copied that article, okay, and whatever. At least 15 people on my network around the developing world to know about that, because we're going to be able to say, there's the landfill, okay. There's the city that we know that wet waste is coming from, okay. We can measure it, okay, and maybe we can get paid, okay, to keep that methane out of the atmosphere, okay? And if we keep that methane out of the atmosphere, I can make the bugs eat that eat that wet waste, okay? And I can feed it, okay? And I'll show you a video, okay, where the chickens are eating that, okay, and the eggs are growing and people are paying for the eggs.
I mean, let me just say something about the business community. I mean, I fully agree. I'm not sure that the businesses we need are going to be at the Business School Salata Institute conference, because at the Methane site in Bangladesh, which I've actually also been to, there's a fantastic project for renovating the site. It was done by, the design was a prize-winning undergraduate thesis by a young female architect in Dhaka, and they're trying to. This is in our little history on the site. They're trying to find funding for that. You know, there are many different levels of community and business engagement, which and that's really, I think that's one of the things that comes out from this work. That they're different scales and different kinds of actors. One thing I should actually...
Can you start the Cambridge old landfill and know whether or not it's sure not leaking at all?
The Cambridge
landfill, that's now a park.
Well,
okay?
one of the things I was going to ask Steve about later was in the class I teach in the fall, which he's going to visit. Does he have any spare handheld methane devices? Because I want us to do a field trip in
Well, we should talk about that.
In
See if we can
Cambridge.
find one for you.
But this is something else I wanted to mention. I mean, this sort of sounds like cross-disciplinary collaboration between the sciences and the social sciences or humanities. I think it is, and it's been great, but it sort of didn't happen because the dean said we want transdisciplinary collaboration and here's a this or that for it. It's just working on projects with complementary perspectives, and that's something I think's really important for the graduate school. The other thing I wanted to say, since I guess some people here may have been teaching fellows during their glorious period at the graduate school, this project has been something that has been really captivating for undergraduates in the college. Yeah. Some colleagues of ours took the map as the assignment in a big government department class on climate policy, and he and I got a sort of big Dropbox link to 110 different microhistories because the kids got really involved in this. I mean, it's a way of sort of making sense of some of the larger global discussions of climate problems.
Thank you for that. I'm Peter Hansen, a historian, and could you say some more about the microhistories or the combination of storytelling or other kinds of archives besides just the map? And maybe if both of you could talk about how, because the map is a visualization of a certain kind of data, what are the other sorts of data that you or the students have used in each of your respective areas?
Well, I don't know if Ju is still here. A wonderful, about to be postdoc in Steve's lab, who's a brilliant climate scientist, actually did a microhistory of an Oklahoma site. And I think the quick answer to the question is eclecticism. Different people will use different methodologies, different sorts of sources, different archives, different newspapers, and one of the practical problems is if we're really going to get 100 small histories every month, this is Harvard. We have to have fact checking and peer review. So, the scope of this is large and it's beyond our current capacity. But the answer to that is whichever source and method is appropriate to the place in question. At one point, Steve talked about a nano history. Yeah, micro isn't a term of art.
It seems.
Sorry?
Use AI for searches.
Well, this is something we've been talking about a lot, and actually, our colleague Thomas Lovo, who was the French climate scientist who's going to be coming over here in a couple of weeks, he and his group in France are using AI for this summer. There's somebody else at the Netherlands Space Research Institute who's doing AI work. But it's a different. AI would. Interestingly, I asked a friend who's a super professional user of whatever it's called, advanced AI. She's a professor of astrophysics at Yale. So I gave her this problem and I said, could you just see what AI will do about finding out what the story was there? Nothing, which pleased me a lot.
It seems like there's a lot of opportunity for industrializing the results that you're getting with this. But we're talking about two satellites up there now, or one satellite and one on the airplane. I mean, how fast can you scan? How often would you have to look? I mean, would you need 100 of your satellites in order to provide a business of monitoring gas lines or,
So it's a very good question, and it turns on what we're actually looking for, because these emissions, so the emission that Emma talked about, it occurred one time and was observed by one satellite.
Right.
It didn't last very long. And that's actually quite typical for the very big ones. They don't most of them don't last very long unless you're in Tajikistan. And so in order to characterize them and really understand what they're doing and why they're doing it, you need to do a lot of surveying. So we don't really know the answer to your question, like how many would you need to blanket them and really determine what their spatial and probability distributions are. We don't really know the answer to that. But more than one.
But just on the gas lines, one of the maps, not worth pulling it up now, but the first map I showed, one of the layers is gas and oil pipelines. So you can, and there are other layers about infrastructure. So there's quite a bit one can do with publicly available data. It's really not worth it.
Is it geostationary?
Is it? Could you do it from geostationary? We would love to do it from geo. There would be a quite expensive undertaking because geo is pretty far away, so you need quite a lot of optical power out there. And usually a geo satellite like this would look at one area, another area like this, so it would actually be scanning. But a geo would be a reasonable approach to try to do it comprehensively. To do the whole world, you need at least 3. So,
why do you, since
Now you get stripes. Is it circles? Can you change?
yeah, we get stripes. We do not see the entire world at this high resolution that our satellite will do. There are satellites that Emma mentioned, the Tropomi, that does see the whole world. And then you have a significant uncertainty about where it is because it's got a big spatial pixel.
I was just saying you could.
I believe Jennifer is about to.
Yeah.
Hi, sorry to interrupt the very exciting discussion, but my name is Rachel and I'm a graduate of the Regional Studies East Asia program. As someone who is neither really a historian or like an environmental scientist, I'm seeing and learning about all of this for the first time. So I guess that really got me wondering. I mean, this is amazing what you've done in mapping out these places. And I've also just can't help but thinking that, you know, we're talking about microhistories, we're talking about storytelling. A lot of what is happening here is very personal in some ways, especially in somewhere like Houston. It's affecting people's lives, right? But at the same time, so many people are not really connected to it. Like for myself, like from a third person kind of perspective, learning all of this for the first time, I'm kind of struggling in some ways to kind of feel more of a personal connection to it, to like understanding, you know, what is the actual impact. And like, I'm just wondering, what are you currently doing right now, for example, to raise awareness about those microhistories or the stories that you've mentioned? And also, how are you connecting more to people to kind of have them realize, I guess, in a sense, not just visually in the mapping sense, but also in the personal kind of embodied experience sense of these very real issues that are happening in our modern day and modern climate?
Well, it's a really important question, and I think one reason that the undergraduates here in the college have been excited about this project is that they do see it in a personal way. I mean, quite a few students in the early project actually chose to look at methane sites which were close to where they had grown up or to where their ancestors had come from. And I think, you know, this is at a very early stage, and the collaboration is at a very early stage. And what I hope for the Histories project is actually we'll have some collaborations with people in the locations. I mean, there's a fantastic newspaper in Dhaka, Bangladesh, which has covered the environment a lot. You know, I would love it if we came to, had an agreement with them that their reporters would do 6 of the microhistories. But I think it is that connection to people's lives and to the consequences of climate change and the other pollutants associated with greenhouse gas emissions that potentially will make the difference to.
Yeah, I'd just like to add one thing quickly. I know we're out of time.
One more question, and I know you had your hand raised.
Okay, so the MethaneSAT project will have a platform on Google Earth Engine. In fact, there's already a sample up there. The MethaneSAT project is producing its own data portal, which will provide transparent access to the type of information that Emma talked about without the histories. And then we have this project of hers that I would like to see grow into or merge with one or the other of those so that it could have a massive audience. It is at an early stage, and this stuff doesn't actually just kind of fall out on you. If you're going to make it really operable and accessible, it takes some time. And right now we don't have data from the satellite yet. We should be getting it this summer. So we have the aircraft data. We should have already gotten that out. So I'm at least a year behind on that. But so the aspiration is to do exactly what you said. And we do have the tools. So we are embedded with Google and Google Earth Engine. As I say, there's if you find your way to sort of the like preview type stuff, or, you know, here's what will be coming in the far future, you can find us there. One more question.
When you first mentioned methane history, I thought you were talking about the kind of curve that you initially produced, which was historic. But as I see, you're doing kind of an archaeology of how the formation got there that produces the methane historically. But my second question is, can methane be transmitted underground? Maybe Exxon has this pipe that goes over to that release. Is there any transfer horizontally if possible?
Yeah, so what Emma said was there are two interstate pipelines converge near there. When they need to adjust the pressures in those pipes, they actually will release at the rate that that was observed to be released. And they're allowed to do that, and I believe they have to report when they do that, but that's actually a permitted step. And as Emma pointed out, if we worked at it, we could probably go back and figure out whether they had an event that was observed. But it could be something else. See, that's the thing. She's right. We don't really know.
But natural gas, which so many people haven't, is methane, or methane. Yeah. But in terms of the big, amazingly important curve that Steve showed. I mean, these micro histories are sort of trying to explain why that happened, why the increase took place, sort of location by location. So they're strongly complementary.
And there's a lot to explain. Those are happening all the time.
Yeah.
This is just a sampling. It doesn't cover that much of the time period.
Well, thank you, Steve and Emma, for your most thoughtful presentations.
Thank you.
I think everybody found it was full of new perspectives and insights, so thank you. So on behalf of the Griffin GSAS, I would like to present you with some tokens of our appreciation for spending time with us and for sharing your insights.
Oh, thank you.
So there was something for you, Emma, and for Steve.
Thank you so much.
Thank you very much.
Thank you.
Thank you. Thank you. Thank you. Thank you.